Hey guys, I hope you're well. We're still talking about multiple regression. There's a lot here. Today what we're going to talk about is a little thing called the residual plot. Let me get my pen open here and I'll show you what I'm talking about. Um, Residual plots are handy little devices we can use to test to see, to take a look at least. Maybe not test, that's probably implies a level of certainty we probably don't have when just looking at these. But it allows us to eyeball our assumptions. So what's residual? Well, if you recall, um, in every model we've looked at, we have a stochastic element that we've included, and that's what really allows us to, well, to not have a perfect fit first of all, um, but also to use the tools of statistical analysis to try to make some conclusions, probabilistic conclusions, and that comes in right here through this epsilon, right, through this error term. We assume that there's random error. In particular, one of the things we assume is that it's normally distributed with a mean of 0. That's not that big an assumption because the intercept term will suck up anything that's off the mean generally. But that it has constant variance, meaning that the variance is sigma squared and that variance is independent of x, of the value of x. In addition, that these are all independently distributed. So epsilon I and epsilon j are uncorrelated generally is what we're some kind of assumption. Not exactly right, but yeah, well, yeah. In any case, we're assuming that they're uncorrelated, that there's no relationship between them. The problem is, much like all of these Greek letters, the reason we use Greek letters to delineate these is we can't say anything totally conclusive about any of these, right? These exist, all these betas and this epsilon, they exist beyond the realm of our observation. They're population parameters. Epsilon is not exactly a population parameter, but it's something that is unobservable. We can't observe this error. So instead, what we do is we use what's called a residual as kind of a backdoor to get it. And our residual, if you recall, is going to be the difference between our observed value of y and our predicted value of y. So yi minus y hat I. And usually, much like whenever we're talking about the real world, we use Roman alphabet. EI is what we call our residual. It's how we refer to it. And EI stands in for epsilon, just like B stands in for beta. And yeah, so we have these residuals. Now, we want for them to look something like this. We want them to be normally distributed. If they're not, right, if they're systematically different, then one of our assumptions is probably bad. So what that means generally is we may have a case of model misspecification. And model misspecification happens when there's something underlying the data, some pattern in the data that we haven't accounted for. And one example we looked at, let me see if I can pull this up, is we looked at the situation where we had a rent from one house to another house. Let me copy this. So, or rent from one apartment to another apartment. And we were looking at New York and Little Rock, and I was using made up data, but still, it'll hold. And this was the data that we had, where the spots here, the diamonds, I mean, are observations. We don't have many. And these are all New York apartments, and these are all Little Rock apartments. And yes, we had a model in which rent was a function of floor space, but city was not included. And it turned out that floor space was acting as a proxy for the city in which it was located. So we worked through it. I recommend looking at an older video, one of the previous videos, if you want to see working through this. Today, what I want to show you is what happens if we plot the residuals from this bad regression. Okay. If we plot this, it doesn't look good. This is what it looks like. What we're supposed to see is no pattern, but what we do see is a pattern, and that's not good. And that's a residual plot can help us with that. Let me use this to break down what a residual plot is, okay? So in our residual plot, we have two axes, as is often the case. We have an axis on the left side here. Right? These are our residuals. And then we have an axis through the middle, which is floor space. Now, the mean residual is always going to be 0. So up here, I talked about the mean error term, right? Where am I? There we go. The expected value of epsilon is 0. I didn't write it like that. What I wrote was that epsilon is normally distributed with a 0 and sigma squared. But that's what this is. This right here is the expected value of epsilon. And that's true not only by assumption, it's also true by the way the model fits our data. Our mean, this 0, is always going to be the average residual. But what you don't want to see is anything that looks like, certainly like this. This is very, very bad to have something like that. I mean, mostly what that tells you is this is fake data. Nowhere in real life do you get a fit that looks quite like that. But what this tells you basically is, well, there's some linear relationships that we're not accounting for that mean that our average residual is still 0, but within these subsets, it's not independent. These aren't independent. So what happens? Well, one of the things we did was we added a dummy variable, and once we do that, we can then get two residual plots, one for each of our variables, which is now a dummy variable and our floor space. And these are what those look like. Let me tighten this up a little bit. And these are good residual plots. Why? Well, for a dummy variable, it always is going to look a little funky. The reason there is that you're always going to have a mass at 0, right? And a mass at 1, meaning nothing in here, because the dummy only takes 0 and 1 values. What you want to see is kind of, between similar bands between the two. You don't want it to be correlated with the dummy, so you want it to be kind of a horizontal cloud, and it kind of is. And that's what we really want. What you want is for this to look like it's a normal distribution, like if you smushed it. You can't see my hands, but I'm smushing my hands together. If you smushed it, you would want it to lump up so you get thick in the middle, around the middle. You want it to be thick in here and thin out as you get to the sides, right? Because that's what a normal distribution looks like. A normal distribution looks like this. So you want it to be, you definitely want it to be a horizontal cloud. You don't want it to be, well, I'll show you what some other bad plots are. And you want most of it to be in the middle with a few kind of out on the ends. You don't want anything to be too far out there. One of the other ones we looked at was the what was it? It was a seafood steakhouse versus was it Italian restaurants. That's right. We were looking at Consumer Reports rating of those restaurants. What does this look like? Well, I colored which one's the Italian restaurants red in the bottom one. So this is what we see in that if we plot that residual, where in that model, this is the model that we were regressing. Let me just write it up here for you. We had score equals beta 0 plus beta 1 times price plus epsilon. And we didn't have a dummy included. And this looks kind of okay. I mean, it's not exactly a horizontal cloud, but it clearly are falling between these bands. It looks like we might have a little case of heteroskedasticity, but we don't have very much data to work with. But you don't see the problem with this categorization until you color code these. And what's the problem here? Well, the problem is that there's an unlikely number of red ones on top that happen to get what are large residuals or positive residuals are lucky in this case, right? They're lucky. Oh, come on, my pen died. Well, that's very unfortunate. But positive residuals are lucky in this case. And negative residuals are unlucky, so that's not good. And whenever that happens, we think that there might be whenever something like this happens, we think there might be a problem. Why? Well, clearly, we have, maybe not clearly, but we can test it. Certainly, we seem to have more blue underneath, more negative residuals for the seafood steakhouses, and more red on top, more positive residuals for the Italian restaurants. And that might be problematic. Okay, still, this isn't a terrible one. Well, I can show you what it looks like when we include. When we added our dummy variable, you get a new, oops, I didn't want to go that far down. Let's see. Add a new dummy variable, and you get a new residual plot that looks like this. We have one on the dummy. It's going to be up here. And again, we have maybe a little heteroskedasticity, but probably nothing major. Yeah, I mean, this is, this could just be random error that it's here, down here. But it's definitely kind of within the same range. And here you can see now we have a much more clustered cloud with 1, 2, 3, 4, 5 above and 1, 2, 3, 4, 5 below for the seafood steakhouses. We got 1, 2, 3, 4, maybe 5 below and 5 above, or 6 above and 4 below for the Italian restaurants. Not bad. So this is the after the dummy, and after the dummy, it looks like our the problem here is that we don't want for there to be a variable that we can observe that's correlated with our residuals, right? That's the assumption, and I didn't mention this earlier in our assumptions, but the assumption is that rho between epsilon and x is equal to 0 for all x. So, or xi for all I guess is what you might want to, something like that. In any case, we're assuming that our error terms are uncorrelated with x, so we don't want to see what we saw in the restaurant example where we have some particular set above and a particular set below. All right, now I want to show you what else you can see from stuff like this. So what I'm looking at here is I'm looking at a problem that you guys have already worked on, hopefully, or perhaps haven't. It's from chapter 16. The data set, it's in the bikes spreadsheet, and it's data on a bunch of bikes with their weight and their price. So we have different types of bikes. So we're gonna, in the problem, which I've recorded a video on, you can go through and look at it. We have we have the opportunity to create some dummies to look at whether the type of bike matters. We look at weight, but one thing, without looking at a problem like this, the problem tells us to include x squared in there. Well, how would you know to do that if it wasn't for the question telling you? Well, here's how you might know, and this is where this sort of thing can be very useful. Well, one way would be to draw a scatter plot, and if you see a scatter plot like this, and this is just a scatter plot of weight against price, you can see that there seems to be a curvilinear relationship. It doesn't look like it's just it looks like a quadratic. I can draw it here for you if you want. Kind of see what it won't let me draw on the chart per se, don't believe, but it looks like we might have, I'll try it, let's see, you gonna let me? Yeah, it looks like we have something that looks like it might be quadratic, meaning that price decreases as weight increases, but at a decreasing rate. Okay, well, let's imagine that you didn't put together a scatter plot. How would you know then? Well, we can run a regression, and if we just do this, where we have a regression where our input, our y's, our price, right? That's our dependent variable. We want to know how price is dependent on weight, and here our dependent variable, or our independent variable, is weight. Have labels, standardized residuals, residual plots. So these are, this is the one we want to check. Standardized residuals, residual plots. And then I'm going to name this price equals weight with resids so that we can take a look at it. Okay, this is what we have. So this is a standard output table. Zoom out a little bit so you can see. And this is what you get if you select those residuals. First of all, down here, we're going to look at the residual plot in a second. Down here, you can see that it gives you, for each observation, which matches horizontally with the data. So if you go back to the data, you can see that we have 19 observations. Imagine those are numbered 1 through 19, and that's what these refer to. You have a predicted price, that's this right here, which is your y hat. Then you have residuals, and then you have standard residuals. Standard residuals are handy because they should be distributed standard normally, so that gives you some idea. A standard residual is just the residual divided by the standard error of the regression, which means that it automatically standardizes them all. What that means is that if you have a standard residual greater than 2 or less than -2, that's kind of an outlier. Because those, remember, if you look on your normal chart, those are very unlikely to happen. Here we do see we have an outlier right here, 2.25. That's not what we're really looking at this for, though. So let me show you the residual plot. Let's go back up here. So here we see we only have one variable. This is actually a simple regression. Our explanatory variable is weight, and these are our residuals. Excel doesn't automatically create the standard residual plot. That can be handy to do. Let me show you how to do that if you want to. If you select this data, you click on it and you right-click, and then you click Select Data. It automatically selects the C2 through, the price equals weight with resids C25 to to C43, which is the residuals. If you can't move around in here, else it gives you trouble. But if you change it to D25 to D43, it'll automatically convert this to standardized residuals instead. You want to change this. Standard residuals. And these just are a little easier to interpret, because what you want to see essentially is everything falling between the -2 and +2 lines. What you also want to see is not something that looks like this. Okay? If you see a pattern like this, that means you forgot something. In particular, if you see a pattern like this, it means you want to include a quadratic term. Okay? Your model form is misspecified. So how do we fix this? Well, let's look back at our data real quick and we can show how to fix this. Okay, what that's telling us is what we need to do. We need to insert a column here which has weight squared. So I type in weight squared, you can just copy and paste this, or if you hold Control D, or if you hold Control and hit D, it'll fill it down. One thing I'm going to check is the correlation here. Don't want to have too high a correlation, although I don't think I'm going to change it in this case. Oh, that's a very high correlation. That's all right. It'll be fine for our residual plot. So let's see. Let's look at our residual plot. Again, to get this, we do our data analysis. We have our regression. Okay. Our input range has changed. It's not D anymore. It's E. Excel, the data analysis doesn't automatically shift stuff over. But now our variables are going to be from C1 to D20, right? Because we have two rows. Weight W squared with resids, and I want it to be labels, standardized residuals, residual plots, all the same as before. Here we go. Okay, now we have two residual plots. It looks like we have some other problems. What are the other problems we have? It looks like we still have a problem with heteroskedasticity. And this is still problematic. I'm not going to, well, I'll show it to you now. What that says is that it looks like the variance in our residuals changes. We have much smaller variance at the high levels, the high weights. So with high weights, we have much smaller variance. At the low weights, we have much larger variance. It makes intuitive sense to some extent, right? Because at the high weights, what you might be talking about is you're talking about a very specific type of bikes. Whereas at the lower weights, you might have very different types of bikes, right? You might have road end performance or something like that in there. And so you might be able to solve this problem by including those dummies if that's what's driving this. Alternatively, one other way to deal with this problem right here is a problem known as heteroskedasticity. That's an A there, so skedasticity, that's a Y. heteroskedasticity means different dispersion, or different, different dispersion, really, different shaking. So we have some heteroskedastic data here. That seems to be some of the problem. Our errors, our residuals are distributed with a smaller variance, and then or with a larger variance, and that variance gets smaller as the weight declines. Another way to solve this problem is to do a non-linear transformation of the dependent variable, which I believe, which I show in the light rail problem. So if you look at the light rail practice problem, you can see that well, I think I can actually show you. Yeah, I'll show you the solution there. When you just have riders equal miles, there's a problem where we have a simple linear regression relating electric light rail systems with the number of riders with the number of miles. And in this model, what we have is a heteroskedasticity problem, right? In that the errors start out small, but as the number of miles gets larger, the variation gets larger. But if instead of using the number of riders, we use the log of riders, meaning that we're talking about percentage changes. And I recommend watching this video for a little more detail there. You can see that what was a bad residual plot becomes a residual plot much more like what we like to see, where we have these kind of horizontal lines there. In any case, I could show you a few more residual plots just so you can kind of get a feel for what these look like. These are from the multiple regression notes, so you can take a look at those notes directly if you like. what we have here, this is a model where we have population or GDP regressed on population, and clearly that's going to have problems. It's not a good idea, not a good model to run. But in particular, you're going to have big errors there. Those errors are going to increase with population because the variance is going to increase because small countries are going to have much smaller errors in their GDP, right? So because the error is going to be multiplied by the number of people you have. If you happen to have a number of very productive people, that's not a huge error in terms of Luxembourg, but if it is a huge number if in terms of China, for example. So you can see that these residual plots do not have the nice horizontal cloud. In addition, this one's a little harder to see, but there's kind of a hump here. This is income on experience, and there needs to be a quadratic term because it increases, income increases with experience, but at a decreasing rate. Okay, last but not least, this is what I wanted to show you guys. This is what you want to see, essentially. This is a good pattern where everything is kind of in a horizontal cloud. These two other examples, this is the non-constant variance I was talking about, also known as heteroskedasticity, and this is the quadratic one, like we just looked at. So, how do you deal with these? Well, we're going to talk a little bit more about how you deal with these when we talk about curvilinear relations in the next video that I record. But one way is just to look at your data, think about what you didn't include, what you did include. Is there categorization that you should take account of, or do you really want to be talking about growth in percentages instead of level changes? Do you need to square something in the case where you have model form not adequate, or you have some kind of curvy relationship? If you include like weight and weight squared, that fixed at least that curve we had in there. We still have, and it revealed that we still had a non-constant variance problem. So yeah, the upshot is these residual plots, they're very easy to get to. Excel does it for you automatically. In the data analysis, when you're in regression, you just click residual plots and it'll show you. And yeah, you can learn a lot just by taking a look at what's going on with your residuals. Ultimately, what we really want to know is do we believe our assumptions? And if we don't, if our model leads us to believe that our errors, as we've built them into the model, are bad, in some to be oversimplistic, but if they're bad, then we want to try to fix that problem. Okay, cool. Hope you guys have enjoyed this. If you have any questions, please leave a comment, econdrd, or shoot me an email at jjdelaney@ualr.edu, and I'll be posting more videos soon. Thanks, guys. Bye.